Kids are dumb. They devour food like black holes and can't even solve easy polynomial equations like these. On the other hand, computers are brilliant, lightning fast, strangely attractive, and best of all, far cheaper than kids. But can they find roots of this polynomial equation? Well, seems like this website was also made by a kid. So today we are going to do what we are best at doing. Not this. We are going to write an algorithm which can find roots of polynomial equations like these. Now before we start diving into the algorithm making, we must first set some goals. Number 1. Our algorithm must find all the real roots of polynomial equations with degree up to 200, like this one. Our algorithm must be precise at alto level, which is 10 to the power minus 18. And number 3, make it fast. Now before you ask why not use formula for each degree just like we do for quadratic, this is for cubic equation, this is for quadratic, and we don't even know what's the formula for fifth degree. We ain't taking this road. As you can see, this curve cuts x-axis at 3 points. Well, the x-coordinate of those points are the roots. Now to make our algorithm, we need a recipe, and we'll be requiring some ingredients. Let's start with the recipe first. If we look carefully, this one and the other ones, you'll find something common in most of them. And it is that around the roots, the value of function changes from positive to negative and vice versa. Newton was a good guy and made calculus, so we asked for his help. He looks at this graph and tells us something. He tells us that look, function changes sign between those two critical points. Hey, wait, what are critical points? Well, those are the points where the curve becomes parallel to the x-axis, or where the first derivative becomes 0, or basically the curve turns around. So now we know function changes sign between critical points, and we already know what happens when function changes sign. We get roots. So we now know the plan to get roots. We find critical points, and to find those, we differentiate the function and find the roots of differentiated function, which give us the x-coordinate of critical points. Wait a sec. So in order to find roots of one equation, we must find root of another equation? That's ridiculous. Why am I doing it? Okay, bye. Thanks for watching. Wait. If we differentiate that function again and then again, we find this line, which is actually very easy to solve for, y is equals to 0. And using it, we can find the roots of this quadratic equation, using which we can find roots of this cubic equation. And we can again climb up the ladder, which we came down by differentiating, and get roots of the original equation. Right? Right. We can and we will. But there's always a but. We are missing something here. Remember I said we will find roots between critical points? So what about these points? They are not between two critical points. What are we going to do then? Well, we'll do some cheating. We will pretend that there exists critical point at the edges of this curve called pseudo-critical points, which will trick our algorithm to think that there might exist a root somewhere in there, which is actually true. And using our trick, we will get these two roots also. So, in summary, we will differentiate until we get linear function, and then we will step up the ladder one by one, finding roots for each level until we get to the final polynomial. Now, this whole time I did not tell you why we need to find critical points when we can just see where the curve cuts the x-axis, quite literally. It's because ideally our computers are blind. Until they check every point on the curve, they won't know where the root lies. So we reduce the search space using our dark ways. Now this was our recipe, and for ingredients we have some cool options. So for finding roots between two critical points, we have two options. The first is again a trick from calculus, Newton-Raphson method. And it's actually quite impressive. You start with a guess, you draw a tangent, pick the x-coordinate where the tangent crossed the x-axis, and then again draw a tangent on the curve corresponding to that x-coordinate. do this again and again and again and again. And before you know it, boom, you are sitting right on top of the actual root with precision and accuracy so high, it makes your mouse blush. But sometimes it can be an actual disaster. For example, like these, when the algorithm straight up chooses an asymptote which meets x-axis at infinity, which crashes our program and we never see the face of our roots. There are many such edge cases where this method fails to deliver. So instead of using Newton-Raphson method, we will be using something the cool guys use: binary search, or bisection method as in our scenario. Here, we divide the graph between two critical points into two equal parts. Now, where do you think the root lies? Yes, it's in the red section, so we throw away the blue section. And now, these 2 points become our new critical points. And we again divide them into two equal parts. And we do this again and again and again until we find the root. Simple, beautiful, majestic. God, I love this. I think we should give this project a name: Son of Hitler. Because this algorithm uses blitzkrieg but on graph rather than on ground. So now we have the idea, we have the computer. So let's cook some math. Let's cook some code. Step 1. Format the polynomial. We will format our polynomial into easy to handle format, an array with just the coefficient and the power for each term. Step 2. Differentiate. Easy stuff. Moving on. Step 3. Write a function to evaluate the polynomial for intermediate step. Since we need our algorithm to be fast, we will not be evaluating polynomial directly like dumb kids. But instead, we'll use a method which reduces our arithmetic steps significantly. And it is Horner's method. Step 4. Writing the function for bisection method. Done. Okay, now it's time to test everything. That's working, that's accurate. Great. What the? Okay, so remember when I said roots may exist between two critical points? But if we look carefully, when our algorithm will check between these 2 points and the other two, it's counting the same root twice. So we add more lines to fix it. And yep, it works fine. So over the next 5 minutes, I tested many more polynomials and it solved them gracefully. But you might ask, what's the limit? 50-degree polynomial, 100, 200, 300, 1000? Well, if you think deep enough, you will realize each step we differentiate, we multiply each term with its own power. So if we take a 10-degree polynomial after 9 differentiation steps, our x will have a coefficient of 10 factorial. So as long as the factorial of degree of polynomial is under the JS limits, we are fine. Now since our project is done, I need to tell you something. Babies, they work on chemicals. Some chemicals use other chemicals to make more chemicals, and the cycle goes on and on. And it's so cool how these chemical reactions are all in sync, perfectly balanced. Where some convert food to energy, some use that energy, and some find more food using that terms. And some overlook all these things and fix if something goes wrong. Honestly, they're worth every penny listed on Amazon.